Hi everyone, we're going to start by looking at section 2.1, which is about angles. Much in the way that chapter 1 was a review of ideas from Algebra 2, chapter 2 is going to be a review of some ideas from geometry. So we're going to start with our first definition. In geometry we talked about ways to measure angles. All of us talked about degrees as one way to measure an angle. Many of us probably already talked about a second way called the radian, but we're going to define what that is right now. So we say that a central angle has a measure of 1 radian if it intercepts an arc with the same length as its radius. So a little bit of vocabulary here to unpack. When we say a central angle, what we mean is an angle whose vertex is the center of a circle. So for example here, angle ABC is a central angle. And we say that this angle has the measure of 1 radian if the length for AB, that's a radius for the circle, is also the same as the length for the arc AC. So what we've done here is we've created an angle measurement that's based on, like an arc length, the distance between the arms of our angle. What we'd like to do next is to develop a conversion between degrees and radians, just like we have different units to measure length, like feet and meters. We have different units to measure angle measure. We have radians and degrees. There are more, but they're beyond the scope of this class. And just like for feet and meters, where we want to have a conversion factor, a way to convert back and forth between those measurements, in trigonometry, we'd like to create a conversion factor as well to convert between degrees and radians. So let's show you guys how we come up with that conversion factor and then what it is. Okay, so let's say we have a circle, and that circle has a central angle that's just going to be a straight line. If you remember from geometry, straight lines have an angle measurement of 180 degrees. And if you also remember from geometry, the circumference of a circle is 2 pi r. So the arc length for half a circle, the arc length from B to C, is going to be half of that, would be pi r. Now let's make a little assumption about this circle in particular. Let's say the radius of this circle is 1. That would mean that that arc length is exactly pi, and that tells us then that 180 degrees is equal to pi radians. And that's what we needed. So since we have that 1 radian is 180 degrees, or pi radians is 180 degrees, we can create the following little conversions. So if we have an angle in degrees and we want to convert it to an angle in radians, we multiply by pi over 180. Or if we want to go the reverse direction, if we have an angle in radians and want to turn it into an angle in degrees, we multiply by 180 degrees over pi. Now let's practice that unit conversion here on a couple of examples. So our first example, we're going to convert 152 degrees to radians. So this is an angle in degrees. To convert it to an angle in radians, we need to multiply it by pi over 180. So one way I could do this is I could take my graphing calculator and do 152 times pi over 180, which gives me about 2.65 radians. Now, oftentimes, when we're describing an angle in radians, we like to describe it in terms of pi. So in this case, it'll be some fraction of pi. To figure out that fraction, what I can do is just take my calculator and do 152 divided by 180. I'm just going to ignore the pi and tack it on at the end, like I've done already. And then I press Math, Fraction, and it'll give me 152 divided by 180 as a reduced fraction. So 38 over 45 pi. Either one of these answers is acceptable, and depending on the directions, it might ask you for an answer rounded to 2 decimal places, in which case the 265 is appropriate, or if the directions ask you for your answer in terms of pi, 38 over 45 pi is appropriate, or if they don't make a distinction, either would be fine. Let's look at another example now where we go in the opposite direction. We take an answer in radians and convert it to degrees. So let's say we want to convert an angle with a measure of 2 pi over 5 radians to degrees. So just like before, we'll start with our angle measure that we know. Now our conversion factor to convert radian to degrees is 180 over pi. So I can multiply these two fractions, but really, let's reduce the pi's out of there to start with. That makes life a little bit easier. So now I'll just go to my calculator and do 2/5 times 180. And make my life a little bit easier, and that comes out to be 72 degrees. Now, the next thing we want to do is we want to relate or talk about the relationship between arc length and angles in radians. So let's discuss how to do that. So let's say we have a central angle that we'll call theta. So that circle, the line through it, is just the Greek letter theta. We often use these Greek letters to represent angle measures, and we use the English alphabet variables to represent side lengths. So if we have a central angle with measure theta in a circle with radius r, then the length of the intercepted arc is given by s equals r times theta, where theta is in radians. Or if theta is in degrees, we'll just add on that conversion factor to convert degrees to radians. So s would equal r times theta times pi over 180. So even if theta is in degrees, we'll just tack on our conversion factor to bump it back to radians, and the formula just holds as before. So let's do a couple of examples now and see how that goes. Okay, so let's do a couple of examples here. The first example here says solve for s if r is 1.4 meters and theta is 0.98 radians. Since theta is in radians, I'm going to use the radian version of my arc length formula. S equals r theta. In this case, r is 1.4 and theta is 0.98. So we'll go ahead and type that into our calculator. That comes out to be a 1.372. And since the radius was in meters, the arc length should be in meters. Let's look at part B. So here we asked to solve for s if r is 3.8 inches and theta is 40 degrees. Since theta is in degrees, we're going to need to use our degree formula, which includes the conversion factor pi times 180. So I have r, which is 3.8, theta, which is 40 degrees, and then my conversion factor, which is pi over 180. So if I go and I type that into my calculator, 3.8 times 40 times pi over 180 gets me about 2.65. And since the radius was in inches, this arc length should be in inches. And then in example C says solve for r if s is 18 centimeters and theta is 2.13 radians. Since the angle measure is given in radians, I know I'm going to use the formula S equals r over theta. I'm going to just start by dividing both sides by theta to get the r by itself. So I will just plug in then 18 for S and 2.13 for r, or for theta, excuse me. And then I'll just type that into my calculator. So that comes out to be about 8.45. And since the arc length was in centimeters, the radius should be in centimeters. And that is it for section 1. I lied about section 1. There's actually a couple more examples that I should do. My apologies. So our next example says find the perimeter of a sector with the central angle of 1.7 radians cut from a circle with a radius of 5 centimeters. So let's draw a picture to kind of represent this. So when we say a sector, what we're talking about is like a slice of pizza. So the sector is here, this like slice of pizza. And the perimeter then of the sector is going to be AB, BC, and AC. Now we're told here that the radius for this circle is 5. So AB and BC are both 5. And then AC is an arc length. So we can use our arc length formula. The central angle in this case was given in radians. So it just can be r times theta. So my perimeter is going to be 5 plus 5 plus 5 times 1.7. So I'll go and type that now into my calculator. 5 plus 5 plus 5 times 1.7. So that's 18.5. And since the radius was given in centimeters, my perimeter is in centimeters. Not too bad. For our last example, we're going to say a car has 18 inch diameter tires on it. If the car is traveling 15 miles per hour, how many revolutions per second are the tires making? So the easiest way to do this is to treat this kind of problem like a dimensional analysis problem, where we're starting with 15 miles per hour. We want to end in some amount of revolutions per second. Now, converting hours to seconds is not difficult, but converting a linear measurement like miles to a revolution is a little bit tricky. The key here is going to be that 1 circumference equals 1 revolution. Because how far does the tire go for 1 revolution? Well, it's going to be the circumference of the tire, right? So like, imagine here's your tire on the ground, and it goes and it spins, and you end up somewhere here. This is going to be 1 circumference that it covered. Because if I take this piece and I like wrap it around, it should be the tire. So that's the trick. Okay? So for us, 1 circumference is going to be 2 pi r. The diameter is 18, so the radius is 9. Okay, so let's start. We have 15 miles per 1 hour. And I'm going to convert hours to seconds first. So I remember when I'm doing a dimensional analysis like this, like you probably did in your chemistry class, the units go diagonal from each other. So hours are going to be up front. And I'm going to have minutes in the denominator. And I know 1 hour is 60 minutes. So when I multiply, the hours cancel and I'm left in miles per minute. Well, now I need to convert minutes to seconds. So again, I know minutes are on bottom, so minutes now have to be on top. And I know that minutes and seconds convert. I know 1 minute is 60 seconds. So when I multiply, the minutes would cancel and I'm left in miles per second. So now I'm going to start, now I'm in per second, right? Like I want. Now I want to convert miles to revolutions. So my conversion factor between miles and or between revolutions and linear distance is in centimeters. So I need to convert miles to centimeters. Okay. So I know that 1 mile is 5,280 feet. Maybe you did know that, maybe you didn't, but that's what it is. And I know 1 foot is 12 inches. And then I know 1 inch is 2.54 centimeters. So let's just kind of recap. When we multiply, the miles and miles canceled, so we'd be left in feet. Multiply again, the feet cancel, so now we're left in inches. Multiply again, the inches cancel, and we're left in centimeters. And my last step then is I know that 2 pi times 9 centimeters is 1 revolution. Again, we multiply again, the centimeters cancel, and what we're left with in units is revolutions per second. So now all I'm left to do is multiply this on my calculator. So I'll do all the numerators first. So 15 times 1 times 1, I won't type in the ones because they don't really do anything, times 5,280 times 12 times 2.54. Oops. Put the whole numerator in parentheses, and then I'll put a division symbol. Now put the whole denominator in parentheses. 60 times 60 times 1 times 1 times 1 times 2 times pi times 9. Close my parentheses and press enter. And okay, so your teacher did something dumb because we're in inches here. So this should be inches here. So I don't need this conversion factor at all. Goodness gracious, Mr. Kulik. So all I'm going to do is go back into what I typed in and not type in the 2.54 and press it again, and I get 4.69 revolutions per second. Excuse me for my mistake. And that does it for section 1.